Welcome to the Neural Implant Podcast, where we talk with the people behind the current events and breakthroughs in brain implants in an understandable way, helping bring together various fields involved in neuroprosthetics. Here is your host, Ladan.
Hello, everyone, and welcome to the Neural Implant Podcast. Today's guest is Cory Inman, and actually, he was introduced to me by a friend and former guest, Avery Beddoes of Loop Ventures, and I completely forgot that he had introduced us. And then I was looking up, where do I know him from? Or, how did we get introduced? So that was kind of funny, but we may or may not keep that first part in the episode. Anyways, Cory studies something similar to Dan Rizzuto of Neotherapeutics, a previous guest on the show as well, and basically deep brain stimulation and its effects on other things like memory. But his specialization is more on the emotional side of things, stimulating the amygdala and what do you get from that. So what he's finding is that it can evoke fear or happiness, all these kinds of things in these patients that have already had these implants implanted. So this is really, really cool stuff. And we talk a little bit about this. So if you like this kind of stuff and you want to learn more about this and potential translational effects of this kind of technology, I highly recommend going to the 2019 Bioelectronic Medicine Forum in New York City on April 4th. This is put on by my good friends, Jim Cavuto and Jennifer French of Neurotech Reports. So I highly recommend checking it out. So if you're interested, go to neurotechreports.com or call 415-546-1259 and just let them know that I sent you. And in this way, you will get a free ebook from Jennifer French, and you'll also be helping support the podcast. So now let's get to the episode. Cory Inman, pleasure to have you on the show. Mutual friend and previous guest, Avery Beddoes of Loop Ventures, introduced us. And I was a bit embarrassed right now because I couldn't find, how do I know you? So it's through this. But you do deep brain stimulation and basically affecting emotions with this. I mean, do you want to explain your work a little bit better than I just did?
Sure. Yeah. Well, first of all, thanks for having me on. I've been a listener for a while, ever since you had one of my colleagues on your podcast, Dan Rizzuto. Yeah, so we worked on the DARPA project. He was kind of the leader of that project, and I was one of the postdocs at one of the sites that made all of that work happen. So yeah, it was really cool to hear him come on and the conversation that you guys had about his new company that's a spin-off from the work that we did, the 8 epilepsy centers did, Neotherapeutics. And I worked on that type of project. We were trying to enhance memory with closed-loop brain stimulation, reading what the brain was doing, and then stimulating in response to a brain state that was predictive of someone not remembering some type of word that they had seen before. So we did some work like that. And I was very interested from some of my graduate work where I helped with a project doing deep brain stimulation for depression with Helen Mayberg. I was very interested in trying to understand what the effects on autonomic arousal you could have by directly stimulating the amygdala at different doses. And that sort of thing has been done somewhat before, but not quite with the advanced methods that we used. And we also were able to do kind of a broader sweep of stimulation amplitudes to the amygdala. And the goal was to just basically test the safety of stimulating the amygdala, because there's a history of amygdala stimulation either provoking seizures and things like that. And so we wanted to test, there weren't that many studies that had shown that. So we wanted to test the safety of that, whether it was going to cause any sort of seizures in these epilepsy patients. So first, I guess, let me back up a little bit and talk about how are we doing this work in humans. So we are really fortunate to work with some of the most incredible people that I've ever met that are going through one of the hardest parts of their entire life, where they have to have brain surgery to try to figure out where their seizures are coming from, because no medications have worked. And basically they can't drive, they can't lead a normal life because they're having seizures on a regular basis. And that's everything from, sort of staring spells, what's known as absence seizures, to full convulsions. And it's really disruptive, and it's very difficult for them to lead a normal life. So because none of the drugs have worked, none of the medications have worked, they are candidates for a surgical procedure that would remove that part of the brain that is causing their seizures. And so we have electrodes in the brain to try to sort of triangulate where the seizures are coming from. And so we have up to 100 or 200 electrodes, electrode contacts, about 20 actually separate depth electrodes for 200 electrodes. And we can both record from those, and that's what's happening on a long-term basis, 24 hours a day, as long as they're in the hospital, right after they have the electrodes implanted, kind of waiting to have seizures, essentially. And so in between those moments, we have an opportunity to ask them if they're up for doing some research. And so it's all completely driven by them. We just ask them if they're up for doing it, and we can both record and in some cases at very low levels stimulate the brain to see what the effects of stimulation might be on emotion and memory, attention and working memory, things like that. So we focus primarily on emotion and memory. And our goal is to essentially try to map out the circuit, test whether the stimulation's safe. And then we wanted to move into some work with cognition, where we're actually stimulating the amygdala at really low levels, below what levels that would cause any type of emotional response, to see if we can actually bias the brain towards remembering information that they had just seen. So that's kind of the breadth of the type of work that we do and the types of patients that we do it in.
Wow, that's amazing stuff. That's like really futuristic stuff. I mean, kind of bordering on the ethical questions as well, I think, right?
Sure, absolutely. Yeah, we think a lot about that. We have lots of conversations about that. Emory has a neuroethics center it's very well placed for having these types of conversations. One of the director of that center is Karen Rommelfinger, who has a big role in the NIH Brain Initiative project and the ethics that go along with that. So we've had great conversations with her about this. And, I've given talks at their neuroethics symposiums and things like that. And it's always a very good conversation. It's a conversation we need to have because these types of technologies are going to keep evolving. And, my stance is that we essentially need to be doing it in patients that really need help. At this point, I'm not anywhere near doing this type of stuff in normal, healthy patients that don't need it. And, we're doing it partially because, we think this is the best model for a human is a human. So you can only understand certain things about how the human condition works and the human brain works by testing and having volunteers give their time and their trust to do this type of work. And we've been very fortunate to have lots of incredible patients that have been willing to trust us to do this type of work and to try to really unpack how the human brain works so that we might be able to help patients that suffer from all sorts of disorders in the future.
Okay. And what kind of numbers, how many patients and how, robust is the data, I would ask?
Yeah. So in one of our projects, the project where we stimulated the amygdala just to look at the dose dependence of the response, we had 8 patients. And that's actually a fairly average number for this type of work. That many centers actually don't have a lot of patients. They may have a patient a month or so. So only about 12 to 20 patients a year. At our center, we actually have 2 neurosurgeons that focus on epilepsy and deep brain stimulation for Parkinson's on a weekly basis, and they sort of trade off. So we actually have a patient almost every week, an epilepsy patient implanted almost every week. So we're one of the busier centers in the country, which is part of the reason that we're part of the DARPA project, because they were looking for the centers that could really collect a lot of data in a sort of consortium across all of these, across 8 different epilepsy centers. And so we test anywhere from 30 to 45 patients a year, depending on whether they're full candidates for the various types of research that we're doing.
Wow, that's pretty cool. So what kind of generalizations can you make from it? Is it very similar? Before we started recording, you were saying that it's quite localized, right?
Yeah, so we can stimulate a very specific part of the brain, and it's very localized. Each contact is fairly small, maybe just a millimeter or 2 in width, and it kind of goes around this electrode that's about the size of a piece of angel hair spaghetti in kind of a ring. And we stimulate between 2 of those electrodes. One is the anode, one is the cathode. And we can directly modulate a very specific nuclei in the amygdala, or we can very specifically modulate one region of the brain. And that's usually what we've been doing so far. There is some interest in stimulating multiple parts of a network in sequence or at the same time to try to see what types of effects those sorts of things have. But we're still trying to understand how all of this works. So we're starting, with just one pair of electrodes at a time and very specific hypotheses based off of animal work. So you asked, how many patients do we have in other projects? There's another project that we've tested 30 patients in over the past 2 years or so. And across all of our projects, we've easily tested 100 to 120 patients over the past 4 years since I started my postdoc. So we have a lot of patients. It's very targeted treatments. And usually we're sticking with very low amounts of stimulation that are below what would be expected to provoke any sort of seizure-like activity in these epilepsy patients. And you asked also, how generalizable is it? Epilepsy patients, their brain is not completely normal, but it's actually, a lot of neurologists really think that it's not necessarily that their brain isn't normal. If their brain completely wasn't normal, then they wouldn't be able to talk and walk and have memories and emotional experiences. It's really that there are specific parts of their brain that aren't acting appropriately, that aren't working how they do in a normal brain. And so it's those parts of the brain that we're searching for, right? That we're trying to figure out the parts of the brain that are provoking their seizures, so that the surgeon can discuss with them the surgical option of potentially removing that part of the brain if that part of the brain is redundant and has some other representation in maybe the other hemisphere of the brain. There are some regions of the brain that you can't really do that with, like what we call the eloquent cortexes or cortices. And that's language regions in the left hemisphere, or motor regions or sensory regions for, the different parts of the body, or primary visual areas, things like that. We don't want to directly affect someone's ability to hear or see or move or talk. And those have very specific representations. And if you damage those with surgery, then it's much more difficult to live a normal life. So, it's a balance of trying to make sure that you're treating the epilepsy, but not causing any harm, just trying to remove the epilepsy.
But you were saying actually before that many of the patients don't even feel anything, right?
Yeah, actually, it's exceedingly rare. Out of all of the patients that we've tested with amygdala stimulation, which I think before I started this work, I thought we would see it much more often than we have. We've only really seen people feel something maybe 2 times out of testing 60 patients or something like that with amygdala stimulation. And, from animal studies and things like that, there's a lot of work that would make you think that the amygdala is the seat of fear, and that it's the area that if you stimulated it, it would cause this big fear response. And, what's interesting is that when we did cause a response, the response was fear. So that's what they expressed, that they were very scared. But actually what was interesting was that they felt like it was like a roller coaster scared, like very scary, but they knew they were in a safe situation. So it was a bit of atypical type of experience. And what's interesting is, when we did that exact same experiment in other people, most of them didn't feel it at all. And we've done other experiments at lower stimulation levels that when we're just trying to enhance memory, where no one has ever reported actually feeling something when we do that level of stimulation. And despite that, we can actually show that we can enhance their memory for a picture that they just saw up to 24 hours later. And so that's what's interesting. In this work, most of the time, patients can't even feel the stimulation.
Wow, that's kind of incredible. So what do you think that means, actually, that some people feel something, some people don't?
I think it has to do with exactly where we're stimulating. So in some cases, there's a lot to unpack here. We don't fully understand it. It's going to take a long time to figure out. But how things rise to consciousness and to conscious awareness is a very big question. And what's interesting here is we're actually directly manipulating the neural circuits. And so you would expect that something would rise to consciousness. But, as many cognitive neuroscientists think, about 80% or something like that of our cognition runs under the hood. We aren't aware of it, and it's just happening. And so the stuff that does bubble up to consciousness, it might have a very specific sort of set of networks that you would have to provoke in order to do that. Or you have to provoke them at much higher levels of stimulation than we are to kind of get the concert of that network really moving in the right direction. Because the other thing is that when you have the brain being kind of a network of networks, maybe you actually have to, in order to get this conscious experience, it has to kind of emerge from a bunch of regions working together in the right sort of pattern. So there's a lot of open questions here. But we think that it has very specifically to do with exactly where you're stimulating, and that there are some pathways that will sort of reach the sort of cortical conscious experience better than stimulating other parts of the brain.
Okay, yeah. So you could be either like just a few hundred microns off, or that it's not strong enough and it's being suppressed. And it might actually be felt or perceived by the body, but it's not coming up to consciousness. So yeah, that's actually really interesting. So what are some of your biggest challenges in your research?
One of the big challenges is making sure that we're always on the right side of the ethics, and making sure that we're always making sure that we're being very, very clear with the patients on exactly what we plan to do, exactly what we're doing at any given moment, giving them all they are fully in control of exactly what we're doing, and making sure that that's very clear to them. That if they don't want us to be there, we stop and we go away. And because they're putting a lot of trust in us, we're going to do everything we can for them. And some of the other challenges is that we still don't know so much, and there's so much to try to figure out. So where to start is a challenge, with what questions to ask to start, because you can start very low-hanging fruit, but you also want to start answering sort of questions that are of the time, that other scientists are interested in. So sort of finding that balance between the sort of scientific questions and the questions that the neurosurgeons want to ask, because they want to help create treatment that will help a bunch of patients with particular disorders like post-traumatic stress disorder or traumatic brain injury or epilepsy. And so kind of trying to strike that balance between asking the mechanistic scientific questions and asking the questions that might lead to a future treatment are exactly the types of things that we want to be doing, but can be challenging sometimes in finding that balance.
Okay, yeah. It is kind of like a tightrope you have to walk across. So you can vary the stimulation based on the sites. And is there other ways that you can like vary the stimulation? I mean, like maybe different waveforms, different currents, or something like this? Or what do you kind of notice with those kind of changes?
Yeah, so we can vary the amperage or the amplitude of the stimulation. We can vary the frequency of the stimulation in lots of different ways. And that's actually another one of the challenges, is that there's so many different parameters that you want to sort of sweep through in order to understand what the effects are. It's almost infinite what you can try to test. And so we have to find ways to constrain that a bit. And one good way of doing that is to go to the animal literature and see what's been done in rats or non-human primates in terms of direct brain stimulation for certain types of effects. And most of our work is informed directly by previous work, actually in some cases from Emory and from our collaborators, where it's been done. The exact parameters that we're doing stimulation in humans have been applied in animal models to show the same type of effect that we're trying to show in humans. So for instance, in our amygdala-mediated memory enhancement work, where what we do is we show people pictures one at a time on a screen for just 3 seconds. And then right after the picture, we stimulate the amygdala in a very specific pattern of stimulation, what we call this theta modulated gamma stimulation. So that's 8 bursts of 50 hertz stimulation that happen in 1 second. So the 8 part of that is the theta part of the rhythm, and then the 50 hertz is the gamma part of the rhythm. We think that that's a good rhythm to stimulate in because those frequencies are frequencies that the human amygdala and hippocampus tend to sort of naturally cycle in when they're processing information. And so that was sort of chosen in the rat study. And, the rat studies were done between 2012 and 2015. And they replicated their work over and over and showed that you could manipulate this enhancement effect when rats are running around a track and then they see an object, they'll go up and sniff it. And right as they leave that object, they stimulate the half of the objects and don't stimulate the other half. And what you can show is in the rats that a day later, their memory is just as good as it was the day before. But that's only the case for the objects that were followed by stimulation previously, when they were first seeing the objects. And so we did that exact same experiment as close as we could be to it in the patients that have electrodes in their amygdala. So that's one way to kind of constrain it, is by animal models. There's a lot more flexibility and freedom to sort of test various types of parameters, to test the safety of them, to test whether they have a beneficial effect. And then we can do those same types of parameters in humans. So in that case, we had to also kind of scale up the amplitude, because the rat brain is about as big as the end of my thumb. And the human brain is both of my hands put together. So the amygdala is almost as big as the entire rat brain of the human. So we have to figure out how to scale the amplitude of the stimulation. And because we had done this previous work looking at how amygdala stimulation is dose dependent, where as you turn up the stimulation, you get a bigger change in heart rate and a bigger change in the amount of sweat on your palms, what's known as skin conductance. We knew the level at which, the sort of threshold at which that starts to, those sorts of responses, heart rate and skin conductance, begin to get provoked. And so we stayed way below that level so that we would know that we're only having an effect on this sort of local circuit rather than having this sort of effect on the actual full emotional experience of the patient.
Yeah, it's kind of interesting. I mean, like on one hand, the animal studies can be a good guide, but at the same time, I mean, the animals aren't able to speak. So the humans, you're able to be like, well, what exactly is going on? Tell me. And we don't have to devise an experiment to figure it out.
Exactly. Yeah. I mean, that's the reason that you need to do this type of work in humans, is because you can ask a human, did you feel that? You can ask a human, did that feel easier? Or did you notice anything? You can ask a human, did you remember that? A rat, you have to devise these experiments to sort of infer that they remembered something and to infer that they didn't feel it or that they did feel it. And so that's why we have to try to have models that can easily translate from rats or non-human primates or mice even all the way up to humans so that we can actually try to understand how these sorts of things that we're trying to develop, these sorts of therapies that we're trying to develop actually affect, the human experience.
Yeah, that's really cool. So what do you think are some of the implications of this research?
One implication that I'm going to be following in my next steps, I'll be moving to UCLA soon, in the next month, is that there's an implication that we could potentially, if we can tune this type of effect, actually have a effect on, helping people remember events, helping people that have poor memory due to some sort of neurological disorder like traumatic brain injury or epilepsy, or maybe even things like Alzheimer's disease and dementia. But those are a little bit far off and kind of tough to treat with this type of stuff because they're neurodegenerative, that there's an actual structural change that's changing over time that we wouldn't expect stimulation to really impact very much. But traumatic brain injury, the brain is mostly intact. It's just not working as it used to because of the trauma. So we think that there may be an opportunity to help those patients by giving them a stimulator that could help them remember certain events that they had in their lives. Because the thing that I'm really interested in is, my background is from graduate school is studying autobiographical memory. So the memory that helps us form our sense of self, that helps us remember our past, those sort of core memories. If you've seen the movie Inside Out from Pixar, they talk about these core memories that sort of make you who you are. And a lot of times those memories are emotional memories. They're memories that we think involve the amygdala, that have stuck in our memory because they are particularly evocative and important. And so important either for our survival in the case of negative memories, or important for our success in the future in the case of positive memories, or just, memories that help us understand ourselves and what we care about. And so I think the most devastating thing about any type of disorder that affects your memory is that you could potentially lose your sense of self because the memories that are important to you aren't sticking because you have a problem with your memory centers. And so one way that we could help with that potentially, and the work that we've done with these patients so far, suggests that you could actually stimulate one experience and then bias the brain towards being more likely to remember that information for longer, which means that they're more likely to be able to think about it again at a later point and make that memory stick. And hopefully it will help their daily life because they'll be able to remember that time that they went on a vacation with their family to New Orleans. And I've literally had patients, describe the sort of things that are really distressing about their epilepsy, in that they'll go on whole vacations and might not remember a significant chunk of that vacation because their brain was acting abnormally. So we think, there's a long, long, long way to go. But my hope is that we can figure out ways of stimulating the brain to help people remember their real world autobiographical experiences. And so that's what I'm going to be trying to take steps towards when I'm working at UCLA by doing controlled experiments with augmented reality and in patients that have these implanted deep brain stimulation and recording devices. These are epilepsy patients as well. And so we're going to try to bring all of that technology together to help us try to be able to test and record from the brain and maybe even stimulate the brain while people do real world things on real world timescales, like weeks to months, and real world spatial scale, the city that you live in, the daily experiences that you have around, going to school or work or whatever you're doing, or the moments with your kid or the moments with your family.
Yeah, that's really cool. This kind of prosthetic, I think, would be really helpful. But I guess maybe the more dystopian future or something like this, what do you think about like affecting the emotions of somebody else, either maliciously or benevolently? What about off-label uses like this?
Those are pretty terrifying. They're not something that I hope for in any way. But as I guess we all know, any technology kind of has a light side and a dark side. And it's our job now to set up the foundation to ensure that the dark side never comes to happen, that we really only do this in the service of helping other people live full, functional, happy lives. And so we have to be very careful about making sure that as we try to understand these circuits and as we try to understand the brain, which is the seat of who we are, as we try to understand that, we have to be very cognizant of how this could be used wrong, how this information can be used in a malicious, dystopian way. I pray that that never happens, and I certainly won't have any part in working towards that type of future. Like I said, my whole goal is to try to help people live full, happy, functional lives. They can make all the memories that they want stick and help them have good experiences in their life. But you're right. I mean, there is potential that if you understand these circuits well enough, that you can modulate people's emotional experience. And that is a very scary prospect if it's done in a malicious way.
Yeah, definitely. But I think you're right, kind of what you talked about in the beginning with the ethics side of things. This is like a very, I guess, controlled process. You're not going to like accidentally get this implanted. It's not like, they have some of those like swiping or like scanning things, like they just scan your credit card that's in your pocket and you can like walk by a turnstile and just like automatically charges you or something like. This is definitely not like that. This is like you have a doctor with you and everything's very controlled. So it probably won't have this dystopian future.
Yeah, well, you certainly have to have a surgeon who's been training for over a decade and often like 15 years to implant these types of electrodes and do this type of work. You have to have all of that in place, and then you have to really want to control someone's emotions. So I hope that our society is past anything like that. I wouldn't even consider it. But it's not something that, you're right, it's not something you can walk through a mall and then all of a sudden you have electrodes implanted in your brain. And, I'm not aware of any non-invasive ways of reaching these deep centers of the brain, even if you actually were wearing a cap. There's not really any ways of directly modulating the amygdala or the hippocampus or the hypothalamus or other kind of key emotional centers of the brain. That being said, there are potentially other ways of modulating emotion through other cortical emotional centers through non-invasive stimulation.
Or through ice cream.
Yes, or ice cream or puppies, spiders, all these things modulate emotional experience on a daily basis. Driving a car, seeing a baby smile, all those sorts of things.
Yeah, for sure. I like to ask this question sometimes, like, what would you do with unlimited funding?
I've gotten this question before when I did something for SFN years ago. At the time, actually, I had a terrible answer. I don't even remember what it was. But I think at this point, if I had unlimited funding, I would get together all of the people that are the world's experts in various types of technology, like augmented reality, and sort of ways of capturing your daily experience. Because what I'm interested in is being able to give some patients that have planted electrodes some devices that they can go around in their real world and play a video game, or essentially something akin to like Pokemon Go in their real world. And then they have to remember what Pokemon they caught. That's the short way of describing it. Of course, it won't be Pokemon because everyone's played that game now. but have them try to remember things from their real world that actually I place or my team places in an augmented sense in their real world. Then from there, we can actually try to test how well you can modulate someone's experience, or modulate someone's memory for their actual real life experiences. Because one thing that is true of what we've done so far is that, we're doing very simple, very, very controlled experiments on a computer screen where patients are just looking at pictures on a computer screen in front of them. They're sitting in a bed. They're not really even interacting with the world in the same way that you or I would on a daily basis. And so one way of we've got to get to a point where we can actually test people's real life memory for their real life experiences if we're ever going to actually understand how memory works in the wild. Because right now we have a really good sense of how memory works in the laboratory, but we do not have a great sense of how memory works in the wild. So I would love to bring together all the sort of tech giants that are trying to figure out how to understand the human experience through data, and to help me figure out how to develop a technology that will allow people to document their experiences, us be able to record from the brain at the same time. And then I also think I would try to get to the point where we can actually do a lot of this brain recording from all the different parts of the brain as people actually move around in the real world non-invasively, because it is quite a hurdle to get electrodes implanted in your brain. And so, I'd like to be able to at least record from people's brains while they're actually doing real life things, just to understand the neural mechanisms of daily life, of making memories in your daily life.
Why isn't that done right now? What would be required to be able to have in the wild recordings?
Well, this is exactly what I'm going to be trying to get going now. Really, what we need are brain stimulation devices that can record from many different parts of the brain at the same time. Invasively, non-invasively would be great, but I've yet to see a technology that can do that beyond scalp EEG, and it's limited in what it can do, what it can tell you about deep structures of the brain. But you could do this with scalp EEG too. I plan to do that eventually when I have my own lab. But you'd have to have, right now what we have is a device called the NeuroPace RNS, or the responsive neurostimulator. And this is placed in the brains of epilepsy patients, the same epilepsy patients that I work with while they're getting monitored before any type of surgery. And these patients get the NeuroPace device when they have seizures that come from multiple places at the same time. And there's a couple other indications for why you would get this type of device rather than having part of the brain. And maybe the patient just doesn't want to have a part of their brain removed and would rather try a neuromodulation therapy, because once you lose brain, once it goes away, you can't get it back. And so these neuromodulation therapies don't necessarily fully cure the seizures, where are many cases where resective surgery can stop the seizures and cure the seizures. What it does is it listens for seizure-like activity in the areas of the brain that have been shown to provoke the seizures from the monitoring that we do while they're in the hospital. And it delivers a little bit of stimulation to that part of the brain to try to stop the seizure, to try to interrupt the synchronization of the brain that is happening in that part when the seizure is starting, and to stop it from spreading any further than that area. And this has been shown to be really effective in reducing seizures and making people have less seizures. And so what we can do is there's a lab at UCLA, the lab that I'll be joining with Nathia Suthana, who's the director of that lab, where they've learned to work with this device. And the company NeuroPace is very interested in trying to help people do research with these types of devices, where you have two depth electrodes or a strip electrode that kind of lays on the cortical surface, and one that goes down into the brain with 4 contacts on them apiece. So 8 total contacts. They're in or around the centers of the brain that tend to provoke that patient's seizures. And what we can do is we can record from some of those electrodes and see what the sort of oscillatory activity is in those different parts of the brain. We can actually also trigger stimulation as people are doing various things. And so what they have there is a virtual reality suite, 500 square foot room that has motion capture cameras all around it. They have the latest technology for virtual reality and augmented reality. So they build tasks where people walk around the room in a fully implanted device. They're not tethered to anything. And they can walk around the room and try to remember different spatial locations, or they can try to remember different experiences that they have in the room. You could do all kinds of stuff. You could have them try, meet a bunch of avatars or something like that, learn some backstory on them in the room. And it's going to be more real life than anything that most people have ever been able to do while recording from the brain and testing the patient's memory. And so basically what I'll be doing is trying to combine augmented reality with devices like the Magic Leap 1, which actually just project, it's kind of like sunglasses, and they just sort of project a 3D image into your environment, whatever that environment may be, your living room or your kitchen, or in our case, this big virtual reality suite. And they can project all kinds of stuff in your room. And so we're going to, I think, have it, our current discussion is whether the type of task we want to do. And I think we're going to have it project butterflies, because butterflies are easily manipulatable. You can really kind of change what they look like, but they're interesting. People would potentially remember them, and a yellow butterfly versus where the blue butterfly was found and things like that. So this is the type of stuff we're going to be doing. We'll synchronize all of that between the brain recording system, and maybe even hopefully at some point we'll be able to test whether when you stimulate half the butterflies and you don't stimulate the other half the butterflies, do they remember the stimulated butterflies a little bit better? And often these electrodes end up in the amygdala and the hippocampus, because that's often an area where the seizures start. So we have electrodes in those parts of the brain with this NeuroPace device pretty often. So my goal, the next couple of years to do this, when I'm doing this second postdoc, is to sort of try to combine all these technologies, and build a platform for doing recording from the brain while people make memories in the real world.
Wow. That actually sounds kind of fun. It sounds like a little playhouse almost, something like this.
Yeah, that's basically what it feels like. Yeah.
This is a really cool conversation. I've really enjoyed it. Is there anything that we didn't talk about that you wanted to mention?
I don't think so. I think this was a really nice, broad conversation that covered a lot of the points that I'm interested in. Yeah, it's really been a pleasure to be on the podcast. It's kind of surreal after listening to so many of the podcasts that you guys have done, but it's been really cool to be a listener and then now to actually have a conversation with you. So I wish you the best of luck with the podcast. And keep them coming. It's been a really great way for me as a neuroscientist that's, stuck in the lab all day, to kind of branch out and learn about other ways that people are approaching the neural interface problem. I didn't have much of a background in any of the sort of peripheral stimulation type work or recording work. And so this has been a really great podcast to listen to for that type of stuff. It's also got me interested in some of the other podcasts. I really, really liked the panel podcast that you did on kind of the ethical and sort of media questions surrounding, neural implants, with Doug Clinton from Loop Ventures and a couple other people. Yeah, that was a really great conversation. So it's pretty cool to be part of that stream of people.
Yeah, well, thank you so much. Yeah, I'm always surprised that people like it so much. And this is the first that I basically take to mean that the podcast replaces your social life. It emulates a social life almost.
Yeah, I'm about to do a cross-country drive from Atlanta all the way to Los Angeles. So I'm going to be having this podcast and other podcast, I'm sure, on blast because I'll be in the car all on my own. So actually, my dog will be in there, but she's not very good for conversation. So yeah, it's going to be a great ride with these types of podcasts.
Yeah, for sure. I actually just did something like that recently. I went from Phoenix to Gainesville, Florida, with a moving truck with my mom. So a little bit better conversations than with the dog, but it was still pretty rough.
My brother will be there for when we stop. He's driving my wife's car, so we'll get it all worked out. So I'm actually very excited for the trip.
Yeah, sounds like it. Cool. Well, thank you so much, Cory. This has been a pleasure.
Absolutely. It's been a pleasure for me as well. Thank you so much, Ladan.
Hey, I hope you enjoyed it. I really liked it. I thought it was really cool. I think we're going to cut it down a little bit because some of the answers were a little bit long-winded, but it's really cool because I love to listen, and it's kind of strange for me to be a podcast host and loving to listen. I love to ask questions that are really long, and I just sit down and pull out my popcorn and I'm ready to go. But I thought this was really interesting. Again, some of the ethical considerations are a little bit, I don't know, it is actually kind of interesting that it has been approved and that there is not much more of an outcry. I went to the neuroethics conference, which preceded SFN, Society for Neuroscience, in November in San Diego. And, we didn't really talk about this kind of stuff too much. And I don't know if those ethicists really knew that this kind of stuff already existed. So it's really interesting stuff. I think next time I go to something like this, I'm going to have to let them know. And it's fascinating stuff. So it's very, very interesting. And it's kind of futuristic. A lot of people wouldn't really believe that emotions, memories, all this can be affected by these stimulations and that it can be modulated, I guess, too. So really, really cool stuff. I love this. And after the recording, we were actually talking about how there's such a big potential for helping a lot of people in translational opportunities. So I think this is really cool. As you know, I'm very interested in translational things and actually not just sitting in your lab and tinkering with stuff, pipetting and implanting animals and everything like this, but actually getting out into the real world and really helping people, like making an impact in the world. And I love this kind of stuff. That's why I have so many entrepreneurs, so many business starters on the cast as well. And I'm really excited to learn more about this. And honestly, a big place I'm going to be learning about this is the Bioelectronic Medicine Forum in New York on April 4th. So if you're not already going, I would highly recommend going, especially if you're interested in this kind of translational stuff, because there's lots of entrepreneurs there with lots of applications, lots of vendors, investors, everything that's needed to basically make things go from the bench to the bedside. And so if you're interested in attending, go to neurotechreports.com or call 415-546-1259 and just let them know that I sent you, that you heard about it here, and that you want to attend, that you want to learn more about translational stuff, actually helping people, and that you want to take on this challenge, and that you're going to be the one that takes on this challenge and actually brings this stuff to market. So if you do that, you're not only helping out the podcast, but you're also going to get some free goodies like On My Feet Again, which was written by Jennifer French. And yeah, so I will see you there in a few weeks. Bye.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.